Hey guys, and welcome back to another A-Level Maths revision video. And in this video today we're going to take a look at some pure Maths 1 revision. So this is first year material. If you're doing the full A-Level, this video probably won't be too helpful for you. It's aimed more at first year students who are preparing to sit the AS exam. So, like always, let's just jump straight into this. I think there's about 7 or 8 questions here. I've tried to pick a nice balance of questions. And like always, if there's anything that doesn't make sense, just leave a comment down below. So let's take a look at the first question. And this is a question to do with circles. So we've got the circle C, which has this equation here. So that's x squared plus y squared plus 4x minus 2y minus 11 equals 0. And part A here and part B technically go together. In part A, we just have to find the coordinates of the centre of C, and part B, we have to find the radius of C. So let's have a go at 4A, but I'm probably going to do these A and B together. So 4A, we'll put B underneath as well. Okay, so how do we begin with a question like this? Well, if you get given the circle equation in this form, like we've been given here at the start of the question, and then we want the coordinates of the centre and the radius, we need to complete the square. And what we do here is we complete the square on 2 separate parts. So what we do is we put the x components together. So what I've got is x squared plus 4x. And now we put the y components together. So I've also got plus y squared minus 2y. And then whatever's left over, that minus 11, we just keep that on this side for now. And this is all equal to 0. And what I'm going to do here now is just complete the square on the x part here. And then complete the square on the y part here. And then just simplify. Okay, and what you'll see is this unravels quite nicely to give us the coordinates of the centre and the radius. So let's start by completing the square here on this x squared plus 4x. Well, we half the coefficient here of the 4x, so that coefficient is 4, so half of 4 is 2, so we get x plus 2. We square all this, and we take the square here of 2, and take the negative of that. So 2 squared would be 4, that would give us minus 4. Now we complete the square on this part here with the y's, so that's going to give me y. We divide this coefficient here again by 2, we half it, so it's going to give me y minus 1. We square all of that, and again we square this term here and take the negative, so that's going to be minus 1 as well. And then don't forget what we've got left over here at the end, so we've got a minus 11 here, okay, and this is all equal to 0. So what I've done there is just complete the square on 2 different parts. So if I highlight that in 2 different pen colours, so this red part here corresponds to this part, and if we do it in blue, this part here corresponds to this part. Okay, and the minus 11 is just left over from both parts. And all we do here now is we just collect like terms. So, or I say collect like terms, all we can actually simplify here is the minus 4, minus 1, minus 11. And that will give us minus 16. And what we're going to do is we're going to take that onto the other side, because remember, for a general circle, if we've got x minus a all squared plus y minus b all squared is equal to r squared, well, the centre, if we call that, I would just write centre here, that's given by this minus a and this minus b. So the centre here would be ab, and the radius is just the square root of r squared. So that's all we're going to do here now. We're going to take this minus 4, minus 1, minus 11 onto the other side to give us positive 16, and I get left with x plus 2 all squared plus y minus 1 all squared is equal to 16. And from here now we can clearly see this, the centre of this circle. Well, my centre here, remember we take the opposite sign, so if this is x plus 2, then my x coordinate for the centre is going to be minus 2. So for the centre, that's going to be minus 2. And for the y coordinate of the centre here, again we take the negative of whatever's here. So if this is minus 1, it's minus minus 1, giving us plus 1. Okay, so the coordinates of the centre is minus 2, 1. And for the radius, remember, we just take the square root of r squared. So we're saying r squared is equal to 16. So if we want the radius r, we just square root both sides, and therefore the radius for part B is simply 4. Okay, remember, we can't take the negative solution here because the radius is length, so clearly it must be positive. So we just get r equals 4 for part B. And let's just clear the screen for now. And let's have a go at part C here. So it asks for the coordinates of the points where C crosses the y-axis, giving your answers as simplified surds. So, where it crosses the y-axis, well, we know it crosses the y-axis when x equals 0. Okay, so that tells us x is equal to 0. So all we do then is we take our equation for the circle, which we know is x plus 2 all squared, just from part A here, and part B, so we got x plus 2 squared plus y minus 1 all squared is equal to 16. And all I do here is substitute x equals 0. So I substitute x equals 0 into this equation. And that gives me 2 squared plus y minus 1 all squared is equal to 16. And all I'm going to do here now is go on to solve for y. Okay, so 2 squared is 4 plus y minus 1 all squared is equal to 16. We subtract 4 off both sides here, so I get y minus 1 all squared is equal to 12. And here now, we take the square root of both sides. Now be careful here. If we take the square root of this 12, we must include the positive and negative solution. Okay. If you think about this circle, if I just draw a really rough sketch here. So what did we say the centre was? Minus 2, 1. So let's just say that's the centre here. What's going to happen is it's going to look something maybe like this. That's not very good. If I say the centre's there, just as a rough guide, then it's going to cut through the y-axis at 2 different points. Okay, it's going to cut through here, and it's going to cut through here. So you should get 2 y solutions here for it cuts through. Okay, and if we just finish from here now, I'll do it in orange. Square root in both sides, I get y minus 1 is equal to plus or minus the square root of 12. And we want to give our answers as simplified surds. So remember, square root of 12, we can write that as root 4, root 3, which root 4 is 2, so this is 2 root 3. Okay, and if I add 1 to both sides, then what we get here is y equals 1 plus or minus 2 root 3 there. Okay, so clearly the solution further up the y-axis here would be y equals 1 plus 2 root 3, and this one here will be y equals 1 minus 2 root 3. You don't need to actually show this in the exam. I'm just showing it here just to kind of further consolidate the knowledge and the understanding, but you definitely don't need to show that. Okay, so that gives us the solution there for our first question. Let's take a look at the next question now. And in this question here, this is from the sample paper. I should have mentioned it, but all papers are given above the question here. So if you want to take a look at them yourself and have a look at the mark schemes, you know where to find them. Okay, so question 10 here. Let's just go back to our original pen colour. Question 10. So we're told the equation kx squared plus 4kx plus 3 equals 0, where k is a constant. And this has no real roots. And it says prove that. So k lies in this inequality here. Okay, so k must be greater than or equal to 0, but strictly less than 3 over 4. Now, when you're doing A-level maths and the AS maths exam like you're going to be doing, you need to be getting good at spotting what kind of topic a question looks like and being able to recognise that almost immediately. So when I see something like this, and hopefully you do as well, you should be thinking straight away, this is going to be a question to do with the discriminant. Okay, and another big clue for that is where it says it has no real roots. Okay, so that tells us we're going to be looking at the discriminant here. So if we have no real roots, so no real roots, well, what that tells us the discriminant, so b squared minus 4ac, is strictly less than 0. Okay, so that's if it has no real roots. So if we take our quadratic equation here and apply the discriminant to that, what we should be able to find here or prove is this result here that we're asked to show for 4 marks. So applying the discriminant then, and we're doing that on this quadratic equation here, so kx squared plus 4kx plus 3 equals 0. So b here will be 4k, so b squared is going to be 4k all squared minus, so minus here, 4ac, so that's going to be minus 4 times a, which is k, and then we times it by c, which is 3. Okay, so times by 3 This is all strictly less than 0. Well, 4k squared gives me 16k squared. And here now, 4 times k is 4k, times that by 3, we get 12k. So this is minus 12k. And this is all less than 0. And just a quick point here, if you take a look at the inequality, it must be greater than or equal to 0. So why is it equal to this 0? Well, if we just quickly take a look at our quadratic again, I can't speak. What happens when k equals 0? Well, if k equals 0, then the kx squared is 0, the 4kx is also 0, and I get a contradiction. I get 3 equals 0. So what that tells us then is that we'll have no real roots. Okay, so when k equals 0, let's make this note here, then this equation has no real roots. Okay, so we will be including that as part of our solution, so it has no real roots. So that will help us for later on. Now, if we come back to our quadratic here, what I've got is a quadratic equation and, I should say, quadratic inequality. So what we want to do now is see if we can factorise this and solve this inequality. Now, taking a look at this, we can factorise this quite nicely by factoring out 4k. So I get 4k here, and inside the bracket, well, what do I times 4k by to get 16k squared? So clearly that'll be 4k. And what do I times 4k by to get minus 12k? And that will be clearly minus 3. Okay, and this is all less than 0. And I would always recommend doing this now with any quadratic inequality. Just do a quick sketch, just so you can see what's actually happening. So if I sketch this here, what I'm sketching now is this quadratic. Well, we have two solutions here. We either have 4k equals 0, so 4k equals 0, or 4k is equal to 3, because 4k minus 3 is equal to 0, so 4k is equal to 3, and k is equal to 3 over 4. Okay, and this should be looking promising now. If you notice, they've got 3 over 4, they've got 0, we've got the same here. Okay, so k is equal to 0. So it cuts through 0 there, and it also cuts through at 3 over 4, say there. Now if we just sketch this here, we get something that maybe looks like this. Not perfect, but we get the idea. And what we're looking for is, where is this less than 0? And this is clearly less than 0. Let me just do this in a different pen colour. Here. Okay. If it's less than 0, it's going to be here. Now, if this was greater than 0, it would be here. So it would be to the left of it, like this. It would be to the right of it, up here. Okay. But because we're looking for less than, this is the one we want. So therefore, to give the solution here, as we already said, k equals 0 has no real roots, so we're going to say that 0, it can be equal to 0. So we just write the solution here from our inequality. This is 3 over 4. This is 0. So therefore, k must lie in this inequality here. As required. Okay, so that gives us the solution there to question 2. Moving on to question 3 here, we have a question taking a look at the factor theorem. So what we've been given here is our function f of x, which is a cubic polynomial. We're told a is a constant, and we're also told that x minus 3 is a factor of f of x. So for part A, this is pretty standard. We just want to show that a is equal to minus 9. So part A here, we're just looking to show that a is equal to minus 9. So the first thing we can start with here is we're told that x minus 3 is a factor of f of x. So if x minus 3 is a factor of f of x, what that means then is f of 3 must be equal to 0. Okay? So in that case, all we need to do now is substitute x equals 3 into our cubic polynomial, and we should be able to show that a equals minus 9. So let's have a go at this then. So what I get here is 2 lots of 3 cubed. So like I said, we're just substituting that into f of x here. So 2 lots of 3 cubed minus 5 lots of 3 squared plus a lots of 3. So in other words, I'm going to get 3a, and then finally we've got the plus 18. And this is all equal to 0. Okay, that's what we said here. F of 3 is equal to 0. And all I need to do now is essentially just solve for a. And what we should find is that a is equal to minus 9. So 3 cubed is 27. Times that by 2, we get 54. 3 squared is 9. Times minus 5 is minus 45. We've got the 3a. And then finally, we've got the plus 18. Okay, and this is equal to 0. Well, 54 minus 45 is equal to 9. So that's equal to 9. Plus 18 gives us 27. So we get 3a plus 27 is equal to 0. So by subtracting 27 off both sides of this equation here, we get 3a is equal to minus 27. And therefore, if we divide by the coefficient of a here, this 3, we get a. And then we need to divide this side as well by the 3. So we get minus 27 over 3, which is equal to minus 9, sorry. Okay, minus 9 there. So minus 27 divided by 3 gives us minus 9 as required. Okay, so that's all we needed to show there for part A. That gets us the first 2 marks. Now part B, there's 2 ways of doing this. There's doing it by inspection, which is the way I'm going to do, because I think it's easy with practice, and once you kind of see how to do the trick for it. The other way of doing it is just by doing algebraic long division. I think that method's tedious, but it's up to you if you prefer doing that way. That is absolutely fine. You'll get your marks that way as well. But let me just show how we do this by inspection. So what we've just essentially shown there is that x minus 3 is a factor of f of x. So what we've got then is x minus 3 times some quadratic here is equal to 2x cubed minus 5x squared plus, so that's ax, so that's going to be minus 9x there, sorry, and then plus 18, okay? Because what we know is x minus 3 is a factor of f of x, so we can split it up as one of our factors like so. Now clearly this is 2x cubed, okay, so this is 2x cubed, so x times something must be 2x cubed. So clearly the first part of this quadratic must be 2x squared. Okay, x times 2x squared gives us 2x cubed. So this part's correct here. And the last term is also really easy to work out. If we just look at the last term here, this is just the 18. Okay, and there's only one way to get that 18, and that's by doing minus 3 times in the last number here in our quadratic. So what do we times minus 3 by to get positive 18? Well, that must clearly be minus 6. So this is minus 6. So all we actually need here now is this middle term, which is arguably the trickiest bit to find, but it's not actually too bad. All we've got to think about here is how do we get this quadratic, or this x squared term here? That's what we're looking for, this minus 5x squared. Well, it can't be to do with this x times 2x squared, because that would be 2x cubed. However, I've got minus 3 times 2x squared, so that would give me minus 6x squared. Okay. And there's only over one x squared term we can get, and that's by doing this minus 3 here, this x here, times by this middle term here. Okay. So for example, if we were to say that was, I don't know, for example, a, okay, ax. So that's ax there. Well, x times ax would give me plus ax squared. And these are the only x squared terms I can get from this expansion. But this must be equal to minus 5x squared. So clearly we can see now minus 6x squared plus ax squared is equal to minus 5x squared. So in that case we can see that a must just be 1. It must be positive 1, because minus 6 plus 1 is equal to minus 5, so therefore a is equal to 1. Okay, so therefore we can write this out now. Part B here, this is going to be x minus 3 times by our quadratic of 2x squared plus x minus 6, but be careful, part B isn't complete here. We need to factorise f of x completely. Well, we can still factorise this quadratic here. So this isn't factorised completely yet. So I get x minus 3 still. And here now, factorising this 2x squared plus x minus 6, this should hopefully be quite straightforward. I'm going to get 2x minus 3 times x plus 2 there. Okay, and that gives us our solution there to part B. So like you can see, you don't need to start doing algebraic long division or anything like that. You can do it by inspection. That's the way I prefer to do it, and hopefully you are familiar with this method. But if you are just confident with algebraic long division, you can just stick to that and get your marks that way. Okay, but that's the answer to part B. And then finally we move to part C here, where it says, given that g of y is equal to this function here, we're asked to find the values of y that satisfy g of y equals 0, given our answers to 2 decimal places where appropriate. Now, when we look at this question here, what you should notice straight away is that between f of x and g of y, they're very, very similar. We've got 2 lots of 3 to the 3y, and in f of x we've got 2 lots of x cubed. In g of y it's minus 5 lots of 3 to the 2y, and in f of x it's minus 5 lots of x squared. In this g of y here it's minus 9 lots of 3 to the y, and in our function here f of x, that's going to be minus 9x, and then finally we get plus 18 in both of them. So they're almost identical. What we're saying here for part C, if we just write this down then, is what we're saying is the thing that's similar between them is that's minus 9x in f of x, and in g of y, this part here, this minus 9 is minus 9 lots of 3 to the y. So essentially all we're saying here is that x is equal to 3 to the y. Okay? So, if x is equal to 3 to the y, and we've factorised f of x already, that's what we did in part B here, we factorised f of x completely, then we can actually go on to find the values of y that satisfy g of y equals 0 really easily. And all we do then is we take the 3 factors that we had. So we had x minus 3, we had x plus 2, and then finally 2x minus 3 equals 0. So let's start with the first one here, x minus 3. Okay, so what we're saying then is x minus 3 equals 0. So x minus 3 equals 0, so therefore x is equal to 3. Now if x is equal to 3, and we know x is equal to 3 to the y, then what we're saying here is 3 to the y is equal to 3. And hopefully the answer here for y should be really kind of obvious, or jumping out here. Y must just simply be 1. 3 to the 1 is equal to 3, so therefore y is equal to 1. Okay, so that's our first solution there for y. We take a look at the next one here then. So x plus 2 equals 0. So what I'm going to do is I'm going to do this in a different pen colour. Let's do this one in red. So x plus 2 is equal to 0. So therefore, solving for x, we get x equals minus 2. And what we said here is x is equal to 3 to the y. So if x is equal to minus 2, what we're saying is 3 to the y is equal to minus 2. But we have a bit of an issue here. And the issue is that we actually have no solutions for 3 to the y equals minus 2. You can think about drawing a graph here just to illustrate this problem and this equation. But for an exponential function like this, we can't solve it. Okay, so therefore, there is no solutions for this one. And then finally, we arrive at the very last one. So again, let's do this in a different pen colour. And this is for 2x minus 3 equals 0. So cut that off here, and we'll do it from the top. So what we're saying here is 2x minus 3 is equal to 0. So therefore, again, just like we did for the others, we're going to solve for x here. So 2x is equal to 3. And therefore, x is equal to 3 over 2. So if x is equal to 3 over 2, all we do then is we take x equals 3 to the y, and we set that equal to 3 over 2 there. Okay, so 3 over 2. And this turns into a problem now of logarithms. And there's two ways of doing this. If you're familiar with the natural logarithm, then you can work this out in a rather straightforward way. If we take the natural logarithm of both sides here, I get the natural logarithm of 3 to the y is equal to the natural logarithm of 3 over 2. The power rule for logarithms states that we can bring this power here, this y, down in front. So I get y lots of the natural logarithm of 3 is equal to the natural logarithm of 3 over 2. And clearly what we want here is just the value of y. Okay, so therefore what I do is I divide by this natural logarithm of 3. So y is equal to the natural logarithm of 3 over 2 divided by the natural logarithm of 3. And if you just put that into your calculator, this will give you your solution now for y. Remember that we want the answer to 2 decimal places. So when I put this into my calculator, I get 0.369. So to 2 decimal places, that's going to be 0.37 there. Okay. The other way is by working with logarithms base 3. You can do that way as well. But either way, you should arrive at the same answer. So it doesn't really matter the base. You're kind of considering whether you're working with the natural logarithm here, base e, or working with base 3. Either way, you should get 0.37 there. Okay. So our 3 solutions, or our 2 solutions, I should say, is y equals 0.37, y equals 1, and then we couldn't get any solutions for this one here. Okay. So that gives our solution there to question 3. Moving on to the 4th question here now, we have a question looking at trigonometry. And in this question here, we have a nice start to it, question 5a. It says, given that 5 sine theta is equal to 2 cos theta, find the value of tan theta. So, if you see something that looks like this, where you've got a trig equation in terms of sine theta and cos theta, and then we suddenly need to end up with tan theta, what you should be thinking of here is that we need to divide through by cos theta. And the reason for that is because we know one of our trig identities is sine theta divided by cos theta is equal to tan theta. Okay, so because we know this identity here, that should be an identity, then we can simply divide both sides of our equation, so 5 sine theta and 2 cos theta by cos theta. So I'm dividing now by cos theta, and again do the same on this side, divide by cos theta. So when you do that, then we get 5 sine theta divided by cos theta is equal to 2 cos theta divided by cos theta. Well, the right hand side here is rather straightforward. 2 cos theta divided by cos theta, they just cancel and you just get left with 2. Okay, so the right hand side here is equal to 2. And on the left hand side here, we've got 5 sine theta divided by cos theta. Well, remember, we just apply our identity here. Sine theta over cos theta is equal to tan theta. So what I've essentially got here is 5 lots of tan theta. So 5 tan theta is equal to 2. Now we just want the value of tan theta, so all I need to do now is divide by the coefficient of tan theta. So we divide both sides by 5, and I get tan theta is equal to 2 over 5 there. Okay, or 0.4 if you're going to give it as a decimal. So that gives our solution to part A. And then for part B here, we're asked to solve for x being between 0 and 360 degrees. 5 sine 2x is equal to 2 cos 2x, giving our answers to 1 decimal place. And what you should notice here is between part A and part B, the equations are almost identical. The only thing that changes is we're not working with theta, we're working with x, and it's 2x rather than just theta. Okay, but the working and the method is almost the same. Obviously this time all we do is we divide by cos 2x on both sides. But you don't even need to show this working. If you think about it, we've just shown there that 5 sine theta is equal to 2 cos theta. If you divide both sides by cos theta, then what you get is tan theta equals 2/5. So if I do the same here with the equation in part B, rather than it just being tan theta, I'm just going to get tan 2x. And that's the only thing that's different. So I just get tan 2x, and it will still be equal to the same thing, which we got was 2/5. Okay, so tan 2x is equal to 2 over 5. So this is for part B. And all I need to do now is go on to solve this equation here. So we just want 2x. So what I do now is I take tan inverse of both sides. So tan inverse of tan 2x. You don't need to go into this much detail that I'm doing here, but just to make it clear what we're doing. And then we take tan inverse of 2/5. Okay. Well, tan inverse of tan, they just cancel. I just get left with 2x. So we get 2x is equal to tan inverse of 2/5. So this you need to input into your calculator. Remember here, we're working in degrees. So make sure your calculator is in the correct mode. You should be in degrees. And what you should get here for your first solution is 21.8 degrees. Okay. Now we're working between 0 and 360 degrees. But that's for x equals. So with this being 2x, all our final solutions we're going to divide through by 2. Okay, so we'll note that here. We're going to divide through by 2. Okay, so we're clearly going to get a lot more solutions. But how do we know the other solutions here? Well, there's two ways of really doing this. You can either draw a graph of tan, or you can use a cast diagram, or you understand how tangent works. So if I draw a cast diagram here, I'm not the biggest fan of cast diagrams, but I prefer drawing them to graphs, but that's because I'm lazy. So what I've got here is my cast diagram. This is C, this is A, this is S, and this is T. So in that case then, as we're working with tan here, that's going to be in the A quadrant. That's for all of the trig functions. And it's going to be in this one here. This is T for tangent, and that would be that angle there. So this angle here, remember we work counterclockwise. So that's going to be that angle there. This is the 21.8. So that's 21.8 degrees. And we also need this solution here. Now this solution is also going to be, or this angle here would also be 21.8 degrees. But to get to there, we just add 180 degrees. Okay. So for every answer you get here, every solution you get, we just add 180 degrees to get the next solution. The reason for that is because tan is periodic about 180 degrees. So it repeats every 180 degrees. So my next solution is 21.8 plus 180. So I get 201.8. Again, I add 180 to this. So my next solution is going to be 381.8 degrees. Now, again, don't worry about this too much. This is 381.8, which is larger than 360. But remember, the x there is just a single x. This is 2x. So some people prefer to double. So that's going to be 0 up to 720. So basically anything up to 720 we're going to include here. So again, we add 180 here. That gives me 561.8 degrees. And if you add 180 one more time, you go larger than 720. So that one would be larger than 720 degrees, and we don't want that. Okay, so we just omit anything past here. So these are my solutions for 2x, but we just want x. So all I do here now is we divide all of these solutions by 2. So 21.8 divided by 2, that gives me 10.9. Remember, give all these solutions to one decimal place. So we get 10.9. 201.8 divided by 2, I get 100.9 degrees. 381.8 divided by 2, I get 190.9 degrees. And then finally, our final solution here, dividing 561.8 by 2, I get 280.9 degrees there. Okay, and that gives us our solutions there for tan 2x equals 2/5, or what we started with was 5 sine 2x equals 2 cos 2x. Okay, but you should get these solutions here. Make sure you don't count these as your solutions. Okay, so that gives us our solution there too. I can't remember what question we're on. Question 4, question 5. I can't remember what we're up to. But let's have a look at the next one. And this is a bit of a lengthier question, or it looks a bit lengthier, but the actual working is not too bad. So this is a question on integration, question 6, part A here. And what I've got is the integral of 10x times x to the half minus 2 dx. Okay, and this integral looks quite complicated, but the actual method isn't too bad. All I'm going to do here to perform this integration is just expand this bracket here with the 10x on the outside. So this is just a simple bit of work with indices. this is 10x, so that's 10x to the power of 1. So when I expand this here, well, this is x to the half, so we're just going to add the powers here. Okay, so what I'm going to get then is the integral of 10x, so that's 1 plus a half, so that's going to be 3 over 2. And we've got minus 2, so when I times that by 10x, I get minus 20x. Okay, and we're integrating this here. So to integrate, all we do is we add 1 to the power and divide by that new power. So if I add 1 to 3 over 2, so that's 3 over 2 plus 2 over 2, so that's going to be 5 over 2. You can do these on your calculator if you prefer, but once you do enough of these integration questions, you'll be really good at adding fractions off the top of your head. So what I get here is 10x to the 5 over 2, and we divide that by 5 over 2. So remember, we divide by the new power. So we divide by 5 over 2. We'll simplify that in a moment. Let's move on to the minus 20x. So again, add 1 to the power, divide by the new power. So I get minus 20x squared, and we divide by this new power of 2. And if we simplify here, well, this left-hand part here, this 10x to the 5 over 2 divided by 5 over 2, well, to simplify this here by hand, we take the 2 and we times it by the 10x. So that would give me 20x, but then we divide by 5. So 20 divided by 5 gives me 4. So I get 4x to the 5 over 2 minus, so this is 20 over 2, giving me 10. So that's minus 10x squared. Okay. And that's it. Pretty much, we're just missing one thing, and hopefully you've also noticed it. Because we have no limits on the integral here, we need our plus c, our constant of integration. Okay, don't forget that. If you do, you're going to lose a mark. Okay, so that's question 6, part A there. And let's have a look at part B here. Now in part B, we're given a sketch of part of the curve C with equation, which what we've actually done there is already integrated this equation. That's what we did in part A. And what we're asked to do then is find the shaded area. Okay, these shaded regions. So this part here and this part here. Now the first thing to note is this is between 0 and 4. This is underneath the x-axis, so that area will be negative. Okay, so when we actually integrate that, we need to take the negation or times it by minus 1 to get that area to become positive. And then for this part here between 4 and 9, that will be positive anyway, so we don't need to worry about that bit too much. So in that case then, it makes sense to split up this integration of 10x times x to the half minus 2 from 0 to 9, and we split this up then as two integrals. So we're going to integrate from 0 to 4 here, that's the part underneath the x-axis, so that's 10x times x to the half minus 2, and then we add the second part here, so that's going to be from 4 to 9, and I'm running out of room a little bit, we should just about have enough. X to the half minus 2 there with respect to x. Okay, you should have a dx there as well. So this is often the case, and this is what you'll do quite a lot of the time, is you'll split your integral up into two different parts. Okay, possibly even 3 parts depending on the function you're integrating, but in this case we only need 2 integrals. So if we start with the first integral here, well, we already know the result of the integral. That's 4x to the power of 5 over 2 minus 10x squared. So we're integrating that, or we're substituting our limits in here. So 4x to the 5 over 2 minus 10x squared from 0 to 4. And if we just substitute our limits in here, I won't go into massive amounts of detail. And remember, this area is going to be negative, so I'm going to take the negation here. I'm going to times it by minus 1. So we're going to get minus. Well, if you substitute 4 in here, so that's 4 lots of 4 to the 5 over 2 minus 10 lots of 4 squared. And if you do that, what you should get there is minus 32. And now we subtract the lower limit. So if you substitute the lower limit in here, this 0, well, that's 4 lots of 0 to the 5 over 2 minus 10 lots of 0 squared. That's just equal to 0. So what I just get there is minus 32. And minus 32 would be 32. Okay, so that's that first part dealt with, the first integral. Now, this part here, again, we already know the result of the integral. That's 4x to the 5 over 2 minus 10x squared. Again, we integrate now, but this time from 4 to 9. Or we substitute our limits in, I should say, from 4 to 9. And if you just put your limits in here, if you put 9 in, then you get 162. So we get 162. And if you put 4 in, we already know that that's minus 32. And remember, we always subtract the lower limit, so this is minus 32. So obviously minus for minus becomes plus. And what I get here is 162 plus 32, giving me 194 there. So I get 194. And to finish with then, we just add our two parts together, 32 plus 194, giving me 226 there. Okay, and that gives the total area of the shaded regions. Okay, so that's our solution there to whichever question we're on. I've actually lost count, I'm not too sure where we're up to, but that's our question on integration. And then finally we arrive at the very last question. Hopefully this video's not gone on for too long, but we have a question here mainly looking at differentiation and transformation of curves. So what we've got here is figure 3, which shows a sketch of the curve with equation y equals f of x. So f of x is equal to a over x plus a half x minus 5. Okay, and what I'd always do here is if you're going to end up differentiating or integrating a function that's written in this form, where you've got, for example, a over x, I just write this in index notation. So that's going to be ax to the minus 1, and then we've just got half x minus 5. Okay, well, in that case, then this is f of x. So if we want the turning point, the coordinates of the turning point here, which is a, then we need the first derivative, f prime of x. And what we do with the first derivative is we set it equal to 0. Okay, so f prime of x, that means we just differentiate term by term here. So ax to the minus 1, so to differentiate here, we take the power and we times it by the coefficient, so I get minus 1 times 8 x, and then we subtract 1 off the power, so I get minus ax to the minus 2. So minus 1 minus another 1 gives us minus 2. If we're differentiating something like this, where it's just x and a constant, then we just get left with the constant here, so I just get a half. And then finally, if you differentiate a constant such as minus 5, this just differentiates to give you 0. Okay, so f prime of x is equal to minus ax to the minus 2 plus a half. So we need to set this equal to 0. So minus ax to the minus 2 plus a half is equal to 0. So what I've got here then is minus a over x squared. So because that's minus, I'm going to take that onto the other side. So I get a over x squared is equal to a half. Now, if we want to solve this, we want to solve for x squared, or solve for x, I should say. So therefore, what I can do here, just to make life a bit easier, is just flip both of these fractions. So I get x squared over 8 is equal to 2 over 1, which is just equal to 2. Times both sides now by the denominator here of 8. So therefore, we get x squared is equal to 16. And to clearly just get x, I just need to square root both sides now. Okay, so we're going up in this pattern here. We'll keep going up. So if I square root both sides, I would normally get plus or minus the square root of 16. But in this case, x must be greater than 0, strictly greater than 0. So we can't have negative 4. X must just simply be positive 4. Okay, now that gives us the x coordinate for the point A. We also need the y coordinate. So if we just do that in a different pen colour here. So for the y coordinate, we just substitute that back into f of x. So that's going to give me a over 4. Remember, x is just equal to 4 here because we want the y coordinate, plus a half of 4 minus 5. Okay, so this is y equals. Well, here now, 8 over 4 is 2. A half of 4 is 2. And we minus 5. So 4 minus 5 gives us minus 1. So therefore, a is equal to 4 minus 1. So that gives us the solution to part A. Now we'll clear the screen here and carry on with part B. Well, it's in a different pen colour just to mix it up. So, 3 different parts here. Part 1, we have to state the roots of the equation 2 f of x equals 0. And the first part, I don't want to say it's a trick question, but there's actually nothing to it. And the reason for that is because when you've got f of x here and you times it by a constant like this, what we do here is we times the y coordinate by 2. So times y quad by 2, or 2 times the y coordinate. But because the y coordinate here for the roots is equal to 0, it's 2, 0 and 8, 0, then we just get the same points. We just get 2, 0 and 8, 0 there. Okay, so the roots don't change for the first part. So that's part 1. Now parts 2 and 3, we do actually have to do a bit of work. So part 2 is asking for the coordinates of the turning point on the curve y equals f of x plus 2. So for the coordinates of the turning point on the curve y equals f of x plus 2, again, with this being outside here, the f of x like this, what we do now is we add 2 to the y coordinates. If it's inside the bracket, it's affecting the x coordinates. If it's outside here, like this, then it's affecting the y coordinates. So in that case then, we add 2 to our y coordinates. So my new points here will be, so what we're doing, sorry, the turning point, we're going to do the roots. So the turning point, well, the original turning point was 4 minus 1. So if we add 2 now to the y coordinate, what we get then is 4 and positive 1. Okay, so that gives us the coordinates of the turning point on the curve y equals f of x plus 2. And then finally, we get the roots of the equation f of 4x equals 0. And this time it is affecting the x coordinates. So this is part 3. So f of 4x is equal to 0. So this does affect the x coordinate now because it's 4x. Now when it's a constant like this times it by the x, what we do is we divide the x coordinates by this constant. So here we divide x coordinates by 4. So because it's 2, 0, 2 divided by 4 is a half. So my first root here is going to be a half 0, or that'd be the coordinates. It would just be x equals a half. And for the next one then, we had originally 8, 0. So if we divide the x coordinate by 2, we get 4, 0. Okay, so we get 4, 0. In that case, we're going to get x equals 4. Okay, but that gives us the roots of the equation f of 4x equals 0. So that gives us the solution to our very final question there and brings us to the end of this A-level maths or AS maths revision video for exam revision. As always, I hope you found this video helpful. If there isn't anything, or there is anything that's unclear, which could possibly be the case, or I've made a mistake, like always, just leave a comment down below. But other than that, good luck in the upcoming exams. I'm sure you'll all smash it. So cheers.